cross sections, and to say that particular nuclei had a cross section of such and such a size for this bombarding particle or that. The effectiveness of slow neutrons was discovered in 1934 by the Italian-American physicist Enrico Fermi, 1901 to 1954. Of course, there was the difficulty that neutrons couldn't be slowed down once they were formed, and as formed they generally had too much energy, according to the new way of looking at things. At least they couldn't be slowed down by electromagnetic methods, but there were other ways. A neutron didn't always enter a nucleus that it encountered. Sometimes, if it struck the nucleus a hard glancing blow, it bounced off. If the nucleus struck by the neutron is many times as massive as the neutron bounced off with all its speed practically intact. On the other hand, if the neutron hits a nucleus not very much more massive than itself, the nucleus rebounds and absorbs some of the energy, so that the neutron bounces away with less energy than it had. If the neutron rebounds from a number of comparatively light nuclei, it eventually loses virtually all its energy, and finally moves about quite slowly, possessing no more energy than the atoms that surround it. You can encounter this situation in ordinary life in the case of billiard balls. A billiard ball colliding with a cannonball will just bounce, moving just as rapidly afterward to be expected at room temperature are called thermal, from a Greek word meaning heat, neutrons. The comparatively light nuclei against which the neutrons bounce and slow down are moderators, because they moderate the neutron's energy. Fermi and his co-workers were the first to moderate neutrons, produce thermal neutrons, and use them in 1935 to bombard nuclei. He quickly noted how large nuclear cross-sections became when thermal neutrons were the bombarding particles. It might seem that hope could now rise in connection with the practical use of energy derived from nuclear reactions. Neutrons could bring about nuclear reactions even when they themselves possessed very little energy, so output might conceivably be more than input for each neutron that struck. Furthermore, because of the large cross-sections involved, thermal neutrons missed far less frequently than high-energy charged particles did. But there was a catch. Before neutrons could be used, however low energy and however sure to hit, they had to be produced. And in order to produce neutrons, they had to be knocked out of nuclei by bombardment with high-energy protons or some other method. The energy formed by the neutrons was at first never more than the tiniest fraction of the energies that went into forming the neutrons in the first place. It was as though you could indeed light a candle with a single match, but you still had to look through 300,000 useless pieces of wood before you found the match. The candle would still be impractical. Even with the existence of neutron bombardment involving low energy and high cross-section, Rutherford could, with justice, feel right down to the time of his death that nuclear energy would never be made available for practical use. And yet, among the experiments that Fermi was trying in 1934 was that of sending his neutrons crashing into uranium atoms. Rutherford had no way of telling, and neither had Fermi, that this, finally, was the route to the unimaginable. End of section 4. Recording by Blaine Aiden McCoy, Riverside, California, January 2019. Section number 5 of Worlds Within Worlds, The Story of Nuclear Energy by Isaac Asimov. This is a LibriVox recording. All LibriVox recordings are in the public domain. To learn more or to volunteer, please visit LibriVox.org. Recording by Blaine Aiden McCoy, Riverside, California, March 2019. Nuclear fission. New elements. In 1934, Enrico Fermi began his first experiments involving the bombardment of uranium with neutrons, experiments that were to change the face of the world. Fermi had found that slow neutrons, which had very little energy, were easily absorbed by atomic nuclei, more easily than fast neutrons were absorbed, and certainly more easily than charged particles were. Often what happened was that the neutron was simply absorbed by the nucleus. Since the neutron has a mass number of 1 and an atomic number of 0, because it is uncharged, a nucleus that absorbs a neutron remains an isotope of the same element, but increases its mass number. For instance, suppose that neutrons are used to bombard hydrogen-1, which then captures one of the neutrons. From a single proton, it will become a proton plus a neutron. From hydrogen-1, it will become hydrogen-2. A new nucleus formed in this way will be at a higher energy, and that energy is emitted in the form of a gamma ray. Sometimes the more massive isotope that is formed through neutron absorption is stable, as hydrogen-2 is. Sometimes it is not, but is radioactive instead. Because it has added a neutron, it has too many neutrons for stability. The best way of adjusting the matter is to emit a beta particle, electron. This converts one of the neutrons into a proton. The mass number stays the same, but the atomic number increases by 1. The element rhodium, for example, which has an atomic number of 45, has only one stable isotope, with a mass number of 103. If rhodium-103, 45 protons, 58 neutrons, absorbs a neutron, it becomes rhodium-104, 45 protons, 59 neutrons, which is not stable. Rhodium-104 emits a beta particle, changing a neutron to a proton so that the nuclear combination becomes 46 protons and 58 neutrons. This is palladium-104, which is stable. As another example, indium-115, 49 protons, 66 neutrons, absorbs a neutron and becomes indium-116, 49 protons, 67 neutrons, which gives off a beta particle and becomes 10-116, 50 protons, 66 neutrons, which is stable. There are over 100 isotopes also be raised in atomic number, in this case from 92 to 93. If that were so, it would be very exciting, for uranium had the highest atomic number in the entire scale. Nobody had ever discovered any sample of element number 93, but perhaps it could be formed in the laboratory. In 1934, therefore, Fermi bombarded uranium with neutrons in the hope of obtaining atoms of element 93. Neutrons were absorbed, and whatever was formed did give off beta particles, so element 93 should be there. However, 4 different kinds of beta particles, different in their energy content, were given off, and the matter grew very confusing. Fermi could not definitely identify the presence of atoms of element 93, and neither could anyone else for several years. Other things turned up, however, which were even more significant. Before going on to these other things, however, it should be mentioned that undoubtedly element 93 was formed even though Fermi couldn't clearly demonstrate the fact. In 1939, the American physicists Edwin Madison Macmillan, born 1907, and Philip Haug Abelson, born 1913, after bombarding uranium atoms with slow neutrons, were able to identify element 93. Since uranium had originally been named for the planet Uranus, the new element, beyond uranium, was eventually named for the planet Neptune, which lay beyond Uranus. Element 93 is therefore called Neptunium. What happened was exactly what was expected. Uranium-238, 92 protons, 146 neutrons, added a neutron to become uranium-239, 92 protons, 147 neutrons, which emitted a beta particle to become Neptunium-239, 93 protons, 146 neutrons. In fact, Neptunium-239 also emitted a beta particle, so it ought to become an isotope of an element even higher in the atomic number scale. This one, element 94, was named plutonium after Pluto, the planet beyond Neptune. The isotope plutonium-239, formed from Neptunium-239, was only feebly radioactive, however, and it was not clearly identified until 1941. The actual discovery of the element plutonium came a year before, however, when Neptunium-238 was formed. It emitted a beta particle and became plutonium-238, an isotope that was radioactive enough to be easily detected and identified by Glenn Theodore Seaborg, born 1912, and his co-workers, who completed Macmillan's experiments when he was called away to other defense research. Neptunium and plutonium were the first trans-uranium elements to be produced in the laboratory, but they weren't the last. Over the next 30 years, isotopes were formed that contained more and more protons in the nucleus, and therefore had higher and higher atomic numbers. At the moment of writing, isotopes of every element up to and including element 105 have been formed. A number of these new elements have been named for some of the scientists important in the history of nuclear research. Element 96 is curium, named for Pierre and Marie Curie. Element 99 is Einsteinium, for Albert Einstein, and element 100 is fermium, for Enrico Fermi. Element 101 is mendelevium, for the Russian chemist Dmitry Mendeleev, who early in 1869 was the first to arrange the elements in a reasonable and useful order. Element 103 is Lawrencium, for Ernest O. Lawrence. Rutherfordium, for Ernest Rutherford, has been proposed for element 104. And Hahnium, for Otto Hahn, 1879 to 1968, a German physical chemist whose contribution we will come to shortly, has been proposed for element 105. Neptunium, however, was not the first new element to be created in the laboratory. In the early 1930s, there were still two elements with fairly low atomic numbers that had never been discovered. These were the elements with atomic numbers 43 and 61. In 1937, though, molybdenum, atomic number 42, had been bombarded with neutrons in Lawrence's laboratory in the United States. It might contain small quantities of element 43 as a result. The Italian physicist Emilio Segre, born 1905, who had worked with Fermi, obtained a sample of the bombarded molybdenum and indeed obtained indications of the presence of element 43. It was the first new element to be manufactured by artificial means and was called technetium, from the Greek word for artificial. The technetium isotope that was formed was radioactive. Indeed, all the technetium isotopes are radioactive. Element 61, discovered in 1945 and named promethium, also has no stable isotopes. Technetium and promethium are the only elements with atomic numbers less than 84 that do not have even a single stable isotope. The discovery of fission. But let us get back to the bombardment of uranium with neutrons research that Fermi had begun. After he had reported his work, other physicists repeated it and also got a variety of beta particles and were also unable to decide what was going on. One way to tackle the problem was to add to the system some stable element that was chemically similar to the tiny traces of radioactive isotopes that might be produced through the bombardment of uranium. Afterwards, the stable element could probably be separated out of the mixture, and the trace of radioactivity would, it was hoped, be carried along with it. The stable element would be a carrier. Among those working on the problem were Otto Hahn and his Austrian co-worker, the physicist Lise Meitner, 1878 to 1968. Among the potential carriers they added to the system was the element barium, which has an atomic number of 56. They found that a considerable quantity of the radioactivity did indeed accompany the barium when they separated that element out of the system. A natural conclusion was that the isotopes producing the radioactivity belonged to an element that was chemically very similar to barium. Suspicion fell at once on radium, atomic number 88, which was very like barium indeed as far as chemical properties were concerned. Lise Meitner, who was Jewish, found it difficult to work in Germany, however, for it was then under the rule of the strongly anti-Semitic Nazi regime. In March 1938, Germany occupied Austria, which became part of the German realm. Meitner was no longer protected by her Austrian citizenship and had to flee the country and go to Stockholm, Sweden. Hahn remained in Germany and continued working on the problem with the German physical chemist Fritz Strassmann, born 1902. Although the supposed radium which possessed the radioactivity was very like barium in chemical properties, the two were not entirely identical. There were ways of separating them, and Hahn and Strassmann busied themselves in trying to accomplish this in order to isolate the radioactive isotopes, concentrate them, and study them in detail. Over and over again, however, they failed to separate the barium and the supposed radium. Slowly, it began to seem to Hahn that the failure to separate the barium and the radioactivity meant that the isotopes to which the radioactivity belonged had to be so much like barium as to be nothing else but barium. He hesitated to say so, however, because it seemed unbelievable. If the radioactive isotopes included radium, that was conceivable. Radium had an atomic number of 88, only 4 less than uranium's 92. You could imagine that a neutron being absorbed by a uranium nucleus might make the latter so unstable as to cause it to emit 2 alpha particles and become radium. Barium, however, had an atomic number of 56, only a little over half that of uranium. How could a uranium nucleus be made to turn into a barium nucleus unless it more or less broke in half? Nothing like that had ever been observed before, and Hahn hesitated to suggest it. While he was nerving himself to do so, however, Lisa Meitner, in Stockholm, receiving reports of what had been done in Hahn's laboratory and thinking about it, decided that, unheard of or not, there was only one explanation. The uranium nucleus was breaking in half. Actually, when one stopped to think of it after getting over the initial shock, it wasn't so unbelievable at that. The nuclear force is so short range it barely reaches from end to end of a large nucleus like that of uranium. Left to itself, it holds together most of the time, but with the added energy of an entering neutron, we might imagine shock waves going through it and turning the nucleus into something like a quivering drop of liquid. Sometimes the uranium nucleus recovers, keeps the neutron, and then goes on to beta particle emission. And sometimes the nucleus stretches to the point where the nuclear force doesn't quite hold it together. It becomes a dumbbell shape, and then the electromagnetic repulsion of the two halves, both positive